All right, so we are beginning the recording and we'll go proceed to the next concept that I really want to give you some background on that are related to parallel programming, right? Again, similar to the previous lecture, it will be a lot more theoretical side, or at least it is a lot of the theory side of things rather than the implementation side of things. And uh we have one example about things that you can do with Rust before we begin. This is basically at the end of last class because of the interest of time, right? We are not able to cover this part, but we do have a code that perform Threadpool, which is basically a pool of threads waiting for tasks to be allocated for concurrent execution. The code is available in threadpool.rs, right? For a quick note, is the implementation randomly pick what tasks you have to finish, and that's generally bad, right? So think of it this way. Let's say you go to shopping, and we will explain what is a thread in this lecture, so this might confuse you. But think of the way you manage the checkout line, right? Anyone here been to macro, for example? So one of the thing about macro that I find as a good example here is like you can have a customer that buy tons of things, right? Because they're running a store, maybe they're running a restaurant, so they buy lots and lots of things. So those people would spend like forever at the checkout line, right? And there's another group of people like us who are just normal consumer. We go there, we buy something, right? I have a macro on the way back home, to be honest. So somehow I dropped by and bought like some vegetable, and in total I have like less than 15 items, right? But the thing is, the if you want one thing that you might have realized is many macro, I'm not sure if it's all of them, but they don't have this line for people that doesn't have, say, greater than 10 or 15 items, and you have to wait behind many people that have a lot of things to check out, right? That's why if you propose a scheduler that say, hey, I'm gonna pick this card randomly and check them out, right? That would be a bad policy. Everyone would be angry, right? Imagine you have to queue up and the the person that do the checkout randomly pick who gets to check out at each time. Everyone will be angry, right? But that's the implementation we have in Threadpool.rs. That's the simplest one, right? We're not gonna discuss the theoretical side of like the queuing theory. How are you gonna wait? What's the best policies? If you're curious about that, feel free to check back with me. But I have to put a disclaimer here. I'm not the expert in queuing theory. Uh, but I can give you some more additional material that if you're curious about, right? How do I manage scheduling? That apply to both computer science and business sense, and it apply to the Threadpool implementation. Again, this might be better than sequential execution, right? In some sense. So parallelism is still good. And the other thing that we didn't get to do the last time is parallel merge sort, right? So we talk about parallel algorithm, right? And we talk about how do we design a good algorithm. So let's first go over merge sort. Is it covered in the SOP, by the way? I just want to double check because basically these slides is to make sure I can cover that again. Anyone not heard about how merge sort is done? Basically, you have an array. The first thing you do is you break them into half, and you break them into half again. And when you merge, you do sorting on the way back, right? And can someone tell me what's the benefit? What is a potential benefit of parallel merge sort? I'm just normal merge sort, actually, sequential merge sort over a quick sort. So the quick sort algorithm, the name seems quick, right? But what would be the the benefit of maybe using a merge sort? Anyone want to take a guess? Because I'm not sure if that's covered in the SOOP, but I feel like that might have been covered. Otherwise, any taker? Anyone want to throw a guess here why merge sort can be better? Yes, actually, that's a great response. In quicksort, there's this thing called pivot, right? And the way you pick the pivot tells you how how are you going to slice things in half. So what if by random chance, every time I pick the pivot, I pick the minimum, like basically the minimum number in my list? What will happen? So what will happen if in quicksort I pick the minimum number to be my pivot? Do I get to break the array into half? It's gonna take longer, right? Because every time you're not reducing in the size, you reduce the size by one, right? What does merge sort guarantee? Is that a pivot actually? Or do I just slice this in half? Yeah, it's guaranteed that every time you do the cutting, you're gonna get two equal chunk, right? So that's why people look into merge sort a lot because it's guaranteed, it's provided this potential guarantee. And let me ask you the second question. Other things that I can do in parallel here. So can I, yeah, each of the subarray, right? That subarray. Sorry, I was whenever I say subarray, it's remind me of like the subarray in DRAM, which is a totally different thing. My bad. When you cut this array into smaller array, each of this can be processed in parallel. So let's implement it, right? So here's a code. We're gonna go through that one by line by line. What is our input? Our input is xs and ys, right? What is a function? Anyone want to take a guess what does this function do? The function called merge. Just take a guess from the name. Don't think too hard. What does the function supposed to do? Yes, it takes the left array called xs, right? And to take the other array called ys. By the way, I'm gonna call this a vector. Think of vector as an array. You merge them into cs, which is your result, into a bigger array, right? Merge the two array, right? So quick thing, whenever you name your function, don't name it function fa, fb, fc. Actually have something meaningful that helps a lot with like code portability, giving it to your friends who need to implement the rest of the code and things like that. That's perfect, right? What does mute stand for? It's mutable, right? That's our output. I want to be able to modify the content by basically merging the content of XS and YS, right? Uh, sorry about the this is supposed to be AS underscore slice. When I copy and paste it go into like the underscore actually go down by accident. It should be underscore. Everything you see the what is it? Subscript is actually underscore empty underscore slice. My bad. Should I should have fixed it. And it was an error on the slide. It should be AS underscore slice. Basically, over here, I have mutable XS and mutable YS. And for we are looping until one of them becomes empty, right? yx is empty or xs is empty, while both of them have something left, what does merge sort do? So how do you merge? So let's say xs is 5, 10, 20, 25, right? And over here ys, so this is xs, this is ys, 4, 12, 18, 19, and 21. Merge sort guarantee that each of these sub array, right, are going to be sorted. So what is the first thing I do in merge sort? Over here, this is xs and this the other array is ys. I am going to compare what? Look at the code, this line. What do I compare? I'm going to compare the first elements, right, and see which one is lower, 5 and 4. Which one is lower in this case? 4, right? So it's gonna be doing this else part, ys is lower, so I'm gonna push ys0 to cs, right? So this is cs. Right? So I'm gonna put 4 in here, right? And then loop around. I'm gonna have ys, we'll get rid of 4. Ys is mutable, so it's okay for me to get rid of the first element. I'm gonna compare again, 5 and 12. In this case, 5 is lower, so I'm gonna put 5 in here. Do this line, right? I push xs of 0 and then get rid of the old first element here. So now xs is 10, 20, 25, ys is 12, 18, 19, 21. So I'm going to put in 10 here because xs, again, the head of xs is lower. And then I'm going to put in 12 because 12 is lower than 20. Put in 18 because 18 is lower than 20. And then put in 19. 19 is lower than 20. And then I'm going to put in 20 here because 20 is lower than 21. And I'm going to get rid of this. This becomes 21. Once it's done, I have ys become empty, right? So it get out of the loop, move to here in the blue part, right? If ys, no, my bad. If xs is not empty, you extend cs with whatever is in xs. So you put in 25 here. Otherwise, if xs is empty, you plug in ys at the end, right? So that's a merge function. Any question here? Any questions here? Is this sequentially done or is this done in parallel? So my question, is this parallel version? Or is this sequentially do merging the list at the same time? It's sequential, right? So this is not the best version of parallel merge sort for sure, because you can, well, you can kind of do this in parallel. If you're curious, you're welcome to do this as a part of your project. One of the student that took the class last year did it. It was awesome. But if you want to try this, also make sure you talk to Jan Kanat because there are some algorithm that he can handpick for you and say, hey, implement that. It's like one of the fastest, right? The parallel part happened here. The one that called msort. Anyone want to take a guess what does msort do? It's merged in parallel, right? How can you do that? Remember our old friend reduce, which basically go to each element, right? Go to each element pairwise. This is perfect because we just do, basically we merge the array pairwise from the left and the right side. So our input is the array we want to sort, right? You break into the left side and the right side, and we can merge. So you create the vector, right? The vector of the elements. Each element is one single item, and you do the reduce. Basically, now you have each item in your array or vector, and then you apply the merge function in parallel. So it starts with element 1, element 2 in your list, and you do the merge. Element 3, element 4, you do the merge, and then you merge them again until you got final version, which is the merged list, right? And that's it. Basically, this is how you can divide the whole vector into two halves until you got each single element, right? And then for each of these elements, you do the reduce function to merge it back. And that's all. So that's it for the things that we didn't manage to cover in the last lecture. And we now will move on to parallel programming, right? So before we begin, I need to kind of talk about this concept of multi-threading. Anyone here heard about multi-threading before? Okay, so if you heard about it before, basically think of a thread, right? So we're not gonna go into the details of what goes into the thread. How can you maintain the thread context? How can the system pick which thread to run? We are doing a super high level conceptual thing here, right? Think of a thread as a unit that can do work in your program. Each thread is assigned to run on your CPU. Let's say you buy a multi-core processor that has 4 core, right? You have CPU 1, CPU 2, CPU 3, and CPU 4, right? And your program, let's say you want to run 2 programs in your machine, program 1 and program 2. And let's say both program is multi-threaded program. It's like Photoshop and I don't know, like YouTube and many other Chrome. Basically, you run Chrome, right? When you run Google Chrome, many of those spawn new threads. So let's say program 1 has 5 threads. Each of these line is a thread, and program 2 has 3 threads here, right? Basically, it means that your program potentially can run 5 things at the same time for the program 1 across all the 5 threads, right? So what will happen if I have more threads than the CPU? Anyone want to take a guess on, for example, in this case, I have 4 CPU. Each CPU is capable of running 1 thread at any given time. I have in total 8 threads, right? So what do you do? Yeah, exactly. So the operating system, Windows, Linux, Mac OS, will pick based on the priority to run these things, right? If you have a critical thread, they're gonna get run first. They will have high priority. And that can be another thread that handling printing, right? Do you care if your printer print your document this right now versus 5 seconds later? You probably don't, right? Unless it's 5 minutes later, then that's when you care, right? So if there's more threads than number of CPU, they'll take turn. They'll take turn running on the CPU, right? And the OS and the hardware will be handling what we call context switch. Context switch is when I switch from one thread to run another. Anyone heard about Intel hyperthreading? This thing called hyperthreading? When you buy a CPU, it can say, hey, this thing support hyperthreading. So hyperthreading is a hardware thread context. Basically, it's a hardware context switch. is really fast, but it can only typically support 2 threads. So it means that in this case, if my processor support hyperthreading, my 4 CPU can have in total 8 hardware threads, right? And they would still take turn, but when they switch, it's really quick. It's a few cycles. Basically, it's like nanosecond quick. Software context switch that's done by Linux, that's a lot slower. That would be microsecond latency. So hundreds and thousands of times slower, but it can maintain many threads, right? The Threadpool concept is a software approach to multi-threading as well, right? So that's it. Basically, as I said, hyper-threading is hardware multi-threading. It means that one CPU can switch between thread 1 and thread 2 really fast, right? And with the concept of threading, it means that you can, first of all, create a parallel program, right? The concept of programming language and parallel algorithm and threading so far. It means that my program can run in parallel. So let's think about how to create it, right? Here are the general steps. Again, we'll go high level. We don't have time to cover everything. If you are interested, please make sure you lobby for the parallel programming class that we are trying to cook up. It's likely to be a special topic class. And I'm sure Ajahn cannot really want to teach that as well. But here are the basic steps. First, this is the algorithm side. You break big problems into sub-problems, right? For example, how can I break merge sort into sub-problems? Anyone have any idea how do I decompose merge sort? We just did it, right? So what did I do? What did we do? So which part is done in parallel? The merging call, right? I can have each element and I call merging in parallel. That's how I can break problems into sub-problems, right? And then once you have the sub-problems or task, somehow you might have heard the term task instead, then you have something like a Threadpool to pick up the task. I have the CPU that's not running, so here, run the task. Run this task here in CPU 2, run this task here in CPU 3, right? So you need to basically build a system to handle how do I assign tasks to CPU. And then I synchronize, right? How do I, once I have the answer to each of the sub-problems, how do I synchronize the results and generate the answer to my big problem, right? So these are really high level steps, right? Any questions so far? Because we're gonna go through some of these, how to decompose the problems in general. How do we assign the worker? What are the tools that you can install on your computer to help doing this? So the first step, as I said, is decomposition, right? From the programmer point of view, these are the key issues. First of all, you have to think about, okay, what can I do in parallel? Go back in the last lecture. How can I parallelize my program? And think about dependency, because every time you create dependency, it means you generate sequential execution. So again, remember Amdahl's law, right? Remember Amdahl's law, right? And the next step after decomposition is, if you look at the PDF of the lecture, there's a slide that said assignment. Let's skip that for now. It's actually too advanced, so let's just forget about it. There's no assignment on that. But let's go to orchestration, right? Orchestration is basically once you have sub-problem, How do I organize all the modification? How do I share resources? How do I synchronize each of the subproblems so I have the final results? And how to make sure it's still correct. If I have dependency, it should be preserved. And how to schedule as many tasks in parallel as possible. And the issue that is always annoying about orchestration is there's going to be a lot of costs that are due to things like synchronization, networking, and dealing with I/O. Basically, going to your disk and things like that because they are slow. And the last step is to map to the hardware. So this can be done by the OS, compiler, and hardware itself, right? So we will talk about some of these examples. And the trade-off here is if you want to map threads onto the same processor, right? If you enroll in the system skill class before, I will preach that cache locality is really, really important, right? Another thing that can kill the performance is communication between each of the threads, right? And do you want to maximize the number of independent threads and have lots and lots and lots of parallelisms and maybe run it on a GPU? So before we talk more about these really high level concepts, I need to talk about the programming model, right? The way you have parallel programming model. And in the world, I can kind of bend that to 3 different models. The first one is probably one of the most common, is shared address space. The second one is likely to be much more common in like IoT. It's called message passing. And so cluster computing, basically when you have a cluster-like setup, right? And the last one is common on the GPU, right? It's called data parallel model. And today we will focus on the shared address space. Today we'll cover the first one. Next week, I'm going to talk about message passing, and I'm going to talk about the data parallel, and then we'll kind of wrap it up with how the GPU exploit data parallelism and make it really fast, right? So hopefully you stick around. It's a lot of new concepts for many of you, but hopefully you stick around because this is where you transition from here's the theory and here's the tools that you can use to implement parallel program on top of what we're gonna force you to do in Rust through assignment 3, right? So the first thing is called share address space. And here's the concept. Basically, sometimes we call this shared memory model, right? Can anyone here tell me what is your understanding of address space? Anyone here heard of the term before, actually? Okay, awesome. So you might have heard about it before. The term address space, it has a lot to do with how do I manage the memory, right? So I'm gonna, as always, I'm gonna have the analogy that compare that to how we live our life, right? So can someone explain it to me? How does the government manage the land? Let's say I want to buy a piece of land. What will happen? So what will happen if I want to buy a piece of land in real life, right? Well, you need to go for, yes, you need to go to the land department, right? You show them the, I want this land. There'll be some previous owner, right? I'm gonna transfer the land. Now you own that plot of land, right? And there's actually a lot of thing about the word address. Well, what does the address tell you? So if I give you an address, it's a location, right? It tells you where does the land located, right? And if you are the owner of the land, what will the government guarantee? Can someone do something on my plot of land? If I own this land, right? Can someone else come in and say, hey, I want to build a house here? No, right? So that's the concept of address space. Exactly the same thing. If I own this range of address, can someone else modify that? No, right? No one can modify things that I own. Can someone else read into that? Can someone come into my house and peek into whatever I'm doing? Again, no, right? That's why I use this analogy because it's exactly the same thing. It's not even, I can even say it's stronger that it's not nice to do that, but it's illegal to do it, right? The government, there's a law that prevent people from coming to my house and build their own stuff, right? Okay, so that's the concept of address space. Anyone want to take a guess why is that a good thing? So why is that good? Hint, think about, let's say I have a computer that runs two programs. Why is having the concept of address space for each program a good thing? Yes, exactly. It prevents random editing, right? My Microsoft Word are not supposed to be able to peek into whatever I'm looking up in Chrome, right? And what would be the exception of that? What would be the exception of this guarantee? So let's say I own a house, right? The only thing that someone can come in and build something on my land is what? I have to allow them to do that, right? Basically, you have to allow them to actually, hey, come in. You can do whatever you want to do here, right? Similar to the ownership system, the share address space. What does share mean? Share means, well, to be able to use the space with others, right? So it means that we talk about multi-threading, right? So if I have a shared address space for the program, and let's say the program has 5 threads, what does it mean for those 5 threads? They share the same address space, right? So they can do whatever you want within that address space. I can have thread 1, so let's say this is my share space, right? I can have thread 1 as a T1, which is thread 1, modify this part. T2 comes in, modify this part, right? And I have T3 comes in later, modify the first part that T1 just modified earlier, right? This is a way for each thread to communicate because I need to know how far have you been doing and what can I help. Think of it as working on a group project, right? So does anyone here buy the idea of like in a group project, communication is a key? I mean, it's true, right? You need to be able to communicate with your friends to work on a project together. So let me tell you one more question. Is it better if the project, the way you break down the tasks, it doesn't require a lot of communication compared to the second project where every time you do something, you need to ask your friend, can I do that? Can I do that? Can I do that? Which one is more efficient? The first one, right? Because you can do whatever you on your own because you design it such that whatever you built here, doesn't really impact whatever your friend's doing much until at the end of the project when you merge, right? Think in the same hat as that when you write parallel program. The lower amount of communication, the better. You still need to communicate, but you want to limit that. Synchronization, basically, this is when you have to communicate. It's done through whatever we call locks or mutex. The lock works the same way as real world lock. That is also share, right? Uh, how does lock work? So let's say I have a, what do I lock? What do I want? Give me an example of things I want to lock. Okay, treasure, safe, right? Food, right? Because I'm fat, I want to eat a lot, right? And I fear someone would steal my food, right? You're in a shared dorm, right? Let's say you're in a shared dormitory, and you just bought some food that you really want to eat later, right? You might want to lock them. So what will happen if you store food in the shared refrigerator and you put lock in it? What will happen? Nobody else can access it, right? Which is a good and a bad thing. So what's the good thing about that? That's a great question. That's a question of why do you share it then, right? So sometimes, so first of all, for example, the fridge example is you have shared resources, right? You can't just buy unlimited number of refrigerator, right? So the good thing is, well, once I lock it, nobody else can eat your food, right? What is the bad thing that comes from it? No one else can use the fridge, right? While you're locking, no one else can use it, right? You serialize the usage. You serialize the use of that shared resources, right? So are you all with me? Basically, lock, enable exclusive access, but at the same time, no one else can use it. So let's go back to the question of like, why do you share it then, right? Uh, Sometime you have to basically communicate the result of your function. Let's say I have a function that uh have input here, output over here, and you want to communicate the output that, hey, that's my output, right? That's my output. So think of it this way. Let's say there's a kitchen in your dormitory. It's a fancy dorm with a full-blown kitchen and a fridge, right? And your friend call you and say, hey, I'm sick. Do you mind cooking something for me and put it on the fridge? And whenever I'm like can get out of bed because I'm not dying, I'll microwave it, right? So the fridge becomes a synchronization point, right? It means that while your friend is recovering, which is a function call, let's say function call recover, don't die, right? So while he's busy with running that function, what is the function call that you're running? You're cooking, right? Basically, that's your function. One person is cooking, the other person is recovering. You cook your food, you put that in the fridge. What is the what what's become of the fridge? It becomes a synchronization point, right? I finish processing my function. Here's the output. I'm going to store it here. The fridge becomes the storage. I'm going to store my results right here. Whenever you're done with your function, which is recovery, comes get your food, right? So that's why you might want to share something. The downside of a lot of sharing, anyone wanted to guess the downside? Like, what if I had to share a lot of things? What would be the downside? Well, with a lot of sharing, it end up with a lot of lock, right? Because every time you modify the variable, you have to lock them, which means what? If you have to lock a lot, what does it mean? It's going to be slow, right? So things are going to be slower if you have to rely on lots and lots and lots of lock, right? To be fair, there are many techniques that have been proposed in hardware, in system to kind of like minimize the impact of lock, and it's still ongoing research. But at the end of the day, it's not gonna make your program faster, right, with locking. So think about whether you have to share. Do you really have to share this? Can you divide and work on the algorithm so that you don't have to share, right? If you leave the cooked food in the fridge without locking the fridge, I can assure you, your friends who are hungry comes in, oh, food, and then they'll take the food, right? I feel like we all ran into that situation before. If you bought something from, I don't know, like a top supermarket and you put that in a shared fridge in the dormitory without your name on it, they'll be gone, right? One example of using lock is using pthread in C. We'll go into the detail a little bit more today. Before that, let's cover rest condition again, right? We've been talking about rest condition, but let's kind of concretely talk about it, right? So let's say you have shared data amongst two threads, thread 1 and thread 2, that wants to access both of the shared data. So what happened if T1 gets hold of the data and want to modify, right? Modifying. I have not finished modifying it yet. So let's say this data is number 4 and T1 wanted to do 4 plus 2. While I'm adding, I don't know the result yet. I don't know that 6. T2 comes in, try to read from it. What would be the value? What would be the value that T2 is reading? While I'm modifying, while T1 is computing 4 plus 2, what data will T2 read? If I assume T1 hasn't finished, it's gonna read 4, right? In theory, what are you supposed to read if T1 happens before T2? If the compute of T1 happens before T2, what are you supposed to basically reading? Are you supposed to read 4 or 6? You're supposed to get 6, right? And that's the problem. That's the rest condition. Basically, that's why we name it rest condition. Both threads rest to the shared data, and one of them miscalculate. And here's another example, right? So I think I used this example before, so I'm gonna go really quickly. Let's say I'm broke. I only have 1,000 baht left in my life, and I drop my ATM card without knowing, and I try to use the bookbank to withdraw 1,000 baht. Right? At the same time, someone found my ATM card and somehow know my PIN, right? So they want to withdraw 1,000 baht. What will happen? And what's supposed to happen? So in this case, what will happen? Or I guess what's supposed to happen? What should happen? My bank account become the shared data between the ATM and my transaction at the bank. So the best thing is only one person should get 1,000. The other one should say, hey, it's already 0 baht. You cannot withdraw, right? So that's what's supposed to happen. So let me ask the possibility. So if let's say I'm a crappy programmer and I forgot to lock things, right? What might happen? What might happen? Think of this. This is thread 1. This is thread 2. What might happen? And let's do the sequence. Thread 1, modify my account. And then thread 2 comes in here, say read account value. Wow, I haven't finished. So both would get 1,000. And what would be the final result in my bank statement? So thread 1 comes in, I'm subtracting 1,000 from my bank account. I haven't finished that subtraction. Thread 2 comes in right at that nanosecond and say, hey, I want 1,000. They're gonna read 1,000. Both people will get 1,000. What's the final value in my bank account? And actually 0. Let me do this timeline a little bit tighter, right? Account is 1,000. Thread 1 comes in. I want to do 1,000 minus 1,000. I haven't finished, right? So it's still 1,000. The value still whole. Thread 2 comes in here. The first thing you do is to read, right? You read this. So what's the value in my account? So I read while thread 1 is still processing. It's still 1,000 minus 1,000. I don't know what's the value yet. So when T2 read my bank account, what is the number I'm gonna see? 1,000, right? Because I haven't finished thread 1. So I'm gonna wait a little bit longer. Thread 1 finish, right? So over here, account becomes 0, right? I'm gonna write the value 0. Thread 2, I withdraw 1,000 again. So it's gonna compute 1,000 minus 1,000. So what's the result of 1,000 minus 1,000? 0, right? So it's gonna say, hey, I'm gonna write 0. In this case, both people have 1,000. Your bank ended up with a buggy code, so they lose 1,000, right? They're gonna lose money, right? So in this case, yeah, bank got robbed, right? So as a programmer, let's say you get hired to fix the bug. What are you supposed to do in the beginning? What are you supposed to do with the account? Make sure T1 finish first. How do I ensure that is the case? So there are two things we learned so far in this class. One is atomic operation, right, which is what Rust used to fix it. You can use atomic, right? So in this case, thread 1 will finish. You can lock them. You can lock when thread 1 comes in, lock the account, do the subtraction, write the data back, so you got 0, right? With me so far? Basically, that's the two possible solutions that we've learned so far, that we have learned so far. Right. There are many other possibility and proposal on how to kind of still retain this, but a common solution is you either lock it or you use atomic operation. You can make a transaction. Same thing here. Right? You do the transaction, make sure you lock the account. So let's talk about the concept of mutual exclusion. In English, what does it mean? What does mutual exclusion mean? So what does exclusive mean? So it's both agree, right? Everyone agree that this is the exclusion. And this is used to prevent race condition by making sure, like if I have the same example with the bank account, I'm gonna get the value of the address. add or subtract some number to it and store that update. You want mutual exclusion, which means that you apply atomic operation, either the 3 operation finish or lock it. So to enforce mutual exclusion, as we learned, we can lock. In C, you can say lock and the mutex name. Mutex name is basically the name of the lock. Think about mutex as the name for your lock, right? Let's say I have a house. The lock for my front door will be a different lock for the one I use for my bedroom, right? The same concept. Lock has name. So you can lock certain locks and you can unlock it. You need to make sure you put in the correct name. When I said critical section here means that this is where share variable is modified, right? And some language has atomic operation support. So you can say things like atomic and put the code in here. Or you can do atomic add, right? For example, there's atomic add operation that you can do. It's going to be atomic. So these are tools, right? Basically, think of these as tools that you can apply to enforce mutual exclusion. And to lock the share region, right? So let's say you have a linked list, right? So what happens if I have to do an insertion to my linked list? So I want to insert this node into this position. What do you have to do? Typically, yeah, you change the pointer, right? Basically, you come in there, it's like, oh, okay, this thing should point where? If I want to insert that, where should it point to? I'm going to use a different color just to be clear, right? This thing will point to here. This thing will now point to here. So now you have 5 items, still the same linked list, right? So while you're modifying this pointer, you want to make sure the first thing you do is to lock, right? Lock this and say node dot next equal to insert node, right? Insert node dot next equal to the next node, and you unlock, right? And next node, you can say next node here equals node dot next, right? So let me ask you this question. This is 3 lines of code, right? I first create a temporary variable to store this node, the location of that node, this one. Do I need to lock this line, or can I move my lock here? Can I move? Should I put a lock at line 1 or line number 2? So if I move the lock to line number 2, will it be correct? Yes, it's going to be still correct, right? Because by that point, I haven't really changed anything. I just said temp equal what, right? And no one used temp, so it's safe to do that. The key here, the second key that you want to make sure is to minimize the code that you need to lock to make your code fast, right? Obviously, you can lock the entire program. So let's say if you have a code to do list, int main, right? Your main function, lock, unlock, what will happen if I do this? Will it be correct? Possibly. Is that a good idea? No, right? So make sure whenever you need to put locks in, make sure first of all it should be correct. Make sure it's correct. But then minimize the area, the number of lines that you have to lock, right? So the second thing I want to talk about is you can do parallel programming in a cluster as well. So anyone here heard about the word cluster before? So cluster, a compute cluster is basically multiprocessor with multiple CPU, right? Each of the CPU has their own local memory, so they can share the memory, right, across the node in the cluster. So if you want to access data on another node, this is called non-uniform memory access or NUMA, right? And running complex program in the cloud is relatively similar, right? So this is basically outside of the scope of this class. I still want to kind of talk about it a little bit anyway. These slides will not be on your exam, but I'm gonna explain NUMA a little bit. So NUMA, think about it this way, it's called non-uniform memory access, right? When you access the memory, it can take a different amount of time, right? And the thing is, when you have a cluster computing, right, you have this thing called off-chip interconnects. Basically, you connect, right? You connect. I'm gonna move on the slide so I can draw things. All right, so bear with me so far. I'm gonna move to the next slide so I can draw things. Here is compute node 1. Here is compute node 2. You have the CPU, and you have the memory, which is DRAM. Okay? And when I share the memory, it means that I can have the CPU here access the DRAM here. I can have the CPU here access my DRAM here. I can have the CPU here access my local DRAM here as well, right? So between access number 1 and access number 2, which one do you think is going to be faster? For sure, number 1. So number 1 is going to be faster. So when you want to do computation in the big cluster, don't forget, if you allocate your data, and it just happened to be mapped right here, don't remember you have to go here before the data comes back here. That can make your program slower, right? So that's the problem with NUMA. The location of your data can impact performance, right? Ideally, you want to map the data to the local processor, right? What if the data is shared among multiple processors, right? What if they're shared among 2 processors? So go back to this. Let's say these data is shared between this CPU and that CPU. Do you have a choice? Can you actually put, is there a best solution here? I mean, at some point, the first CPU have to access the node 2's DRAM, right? So in that case, there's still quite a bit of the research going on into how to do this mapping. That's why I said this is basically out of the scope of your class. But I want to really teach it because the reason is when you need to program things in the cloud, remember this might happen to your program. Most of the time, AWS, Google Cloud, Microsoft Azure, they'll manage this for you and they'll try to make sure your data is mapped to a local processor. But sometimes you have shared data, right, among multiple processors. The second scenario is, what if a node has 10 gig, let's say 16 gigabyte of DRAM, and your program demands 20 gigabyte. What do you have to do? What are you going to do with the remaining 4 gigabyte of DRAM that you need to allocate? So let me repeat the question. Let's say I have cluster 1, node 1. Let me address this. Let's say I have a compute node 1 and node 2, and this has 16 gigabyte, this has 16 gigabyte. Your program demand 20 gigabyte. So you will have to allocate it on the other node, right? You basically have to store them in the other node. So this can impact performance. Things like the way you interconnect topology, it means that how you connect the node together can impact performance. How you balance out this 4 gigabyte, where do you want to place it, impact performance. So many things can impact performance in the cloud setup, even though you launch thing in the cloud and you think, hey, it's going to be parallel, it's going to be awesome, it's going to be fast. You might run into some of these issues, so you have to configure this a little bit, right? Again, not going to be appearing on the exam, but it's a high chance you might run into this in real life, right? So that's why I put it here. So let's come back to the context of our class. So anything from here onward can be on the exam. So what is a parallel 2 library that we can use in Rust for parallel program? Anyone remember? Rayon, right? So that's your friend. Simple, powerful, fast, and hopefully relatively fewer bugs. I'm not going to talk too much about it because I already talked about it for 2 lectures last week. By the time assignment 3 comes out, which is basically next Tuesday, actually next Monday. Next Monday, I'm going to release assignment number 3. You get to try it, and hopefully you get to practice for the project, right? And again, the concept of threading, as a higher level, it runs parts of your program. One thread can run an entire program. Multiple threads can work together to run a program. Sorry. Right. One program can consist of one thread. That's fine. Is likely to be most of the program that you've been coding so far. That's one thread, single threaded program. But program can be running with multiple threads, right? And we're not gonna go deeper into this at all because more information plus the practice are gonna be available in the first of all the Comsys arc with the basic stuff. You're going to use pthreads and you are likely to get sick of pthreads. The OS class, again, more pthreads. You get to run parallel program, but from the management point of view, you will learn in the architecture class. So the OS and architecture class are not required, but if you're curious, in the architecture class, we'll talk about how do we run multi-core and how do we map these threads, right? And the first 2 before Rust, before the dawn of like parallel programming, right? You have these days you have OpenMP, you have Rust, you have Scala, you have GPU. Before that, there's this thing called POSIX threads. Anyone know what POSIX stand for? It actually stands for Portable OS Interface. Right? What does portable mean? What does it mean for things to be portable? Yeah, it's easier to transfer around, right? So it's a IEEE standard maintained by TOS, and it defines the API, right? Application Programming Interface. This allows you to run basically multi-threaded program from one machine to another, right? We can use pthread in C. It will use POSIX standard. Pthreads stand for POSIX threads. And by compiling your code and adding -lp thread in GCC, when you compile the C code, it would allow the use of pthreads. We're not going to cover this because you're going to get to practice it in Consistorg. If you haven't taken the class, it's fun. If you are taking the class, hopefully it's fun. If you took the class, hopefully it was fun. All right, but we'll cover this in different class. What we will try to cover here is OpenMP. Anyone here heard about OpenMP? So we are not going to do assignment on this, but I'm going to point to a good, possibly study material if you want to try out OpenMP. So we're going to have this non-mandatory in-class exercise on OpenMP. But it might take a longer time than a typical in-class exercise. So that's why I said it's non-mandatory. So I'm not going to put it on the class website. It's just on the slides, and I'll tell you, hey, try these things. OpenMP is a library. When you install, it's designed for parallel program, specifically for symmetric multiprocessor. Multiprocessor means multi-core. What does symmetric mean? Yeah, it looks the same. Basically, each core looks the same. Same clock speed, same architecture, right? These days, I think the assumption about the clock speed can be relaxed a little bit. Right? So you can have something like the M1 processor in Apple, where you have a bigger processor next to a smaller processor, that's fine. And assume share memory, right? Again, in this case, share memory is your friend. Once you install it, you can put a mark on your code in the region that you say, hey, this can be done in parallel, right? Basically, the mark can be done by putting in the pound sign, pragma. Pragma is basically giving hints like, hey, compiler, this is my hint to you. The hint is use OpenMP, and then you can add whatever you want to do here. For example, if you want to run a for loop in parallel, you can use OpenMP4. OpenMP4 will trigger run this loop in parallel. So what's the benefit of this? What's the beauty about what you've seen so far? Is it simple? Yeah, it is actually pretty simple to try, right? So you can run things in parallel really, really relatively easy, right? And when you compile your code, just say -f-openmp. That would make sure the compiler seek for this pragma OMP, and it would run that in parallel, right? Compared to pthreads, this is a lot easier. It is a lot easier. But at the same time, when you have these tools, what is the only what's the one thing that you still need to consider? Algorithm, right? You need to make sure your program can run in parallel before you use it. More information, you can go to openmp.org/resources. And inside that link, there's a tutorial. So this is more on the actual exercise organized by one of the senior scientists at Intel. They're working with OpenMP organization to actually allow you to try. There are the thing about 20 or 30 video clips, and each clip is about 10 minutes long. So it's not long at all. You can start and see if you'd like it or not. And if you're curious about it, let me know, right? So I can troubleshoot things that you get stuck if you try to implement something such as our non-mandatory exercise. So it's basically try out OpenMP by running, first of all, well, I have two array of equal size. Can I add the two up in parallel, right? These should be really, really, really easy. Fibonacci should be also quite easy, but then when you run Fibonacci, it will not be really, it will be faster, but it will not be very fast. The reason behind that we developed it last lecture, which is Fibonacci is gonna end up spending a lot of time on one side of the function call, right? Definitely feel free to check out the OpenMP tutorial. And that's it for the lecture part today. So I'm gonna pause the recording right now.